Okay, good afternoon, everybody. Okay, today's sessions will be on the electrical worksheet that I given to the class. Okay, it's on this particular worksheet. So I'll run through the solutions for all the questions. So because of I'm going through all the questions, this particular video will be quite lengthy. So for those who are only having problem at certain questions, I will advise you to go and skip the video to maybe the necessary locations or the location necessary part, so that you can just view the video for the questions that you are in doubt. Okay, so don't just watch it from like at the beginning all the way to the end, because it will be very boring and it will be very lengthy. Okay, so only watch the segment that you are interested in. Okay, so without further delay, okay, we'll look at the worksheet that I have given to you in class. Now, the worksheet that I have come up with, okay, so far what we are looking at is to apply the basics of electricity, how to analyze the circuit and how to actually deduce the formulas or how to calculate the unknowns that's given in the circuit. So some of the basic things that we cover is under the basic section here. Okay, under the basic question, what you're looking at is you're looking at like you should get all the basic questions correct. Okay, because that's what we are looking for, the basic of series, parallel, and V, I, and R. Okay, so for question 1A, what we are looking at is a circuit. Okay, now for this circuit here, just a side note is that you are looking at this particular resistor. Okay, and you have one pair of resistor that is in up and down formations. So this is what we call the resistor are in parallel. Okay, and this set of resistor is what, when after summing it, we will have this thing called R parallel, the effective resistance of this particular two branch. Okay, then the R parallel will be in series with this particular resistance. Okay, so this is what we call the basic of the circuit. When you look at the circuit, first thing that jump to you should be the arrangement of the resistance. Okay, now for this question here, okay, we are looking at the current that's in the circuit. Okay, the current that coming out from the battery, which is IT. Okay, when it flow through the resistor, so let's say I give it a name. This is resistor 1, resistor 4, and this is resistor X. Okay, now when the current IT flow from the battery, it will flow through the resistor 1. Okay, so this current here will be IT also. And after that, at this node here, at this junction here, the current will be split, okay, into two different paths. At the other side of the node we are looking at, it will join back, okay, and it will come out again. This will be IT. Okay, this is what we mean by the circuit in the series circuit is actually constant. So one of the cue here you are looking at is that the current actually is the same throughout the circuits. Meaning, if you look at the circuit, if you sum all the resistors together, you will have what we call the total resistor. Okay, the current flowing in this total resistor will actually be the same, IT followed by IT. Okay, now what happened to the individual branch? Wait, inside the individual branch is a basic splitting of resistors, current. So what we have is the current IT will be flowing here and it will split into two particular paths. So in simple mathematics, you will see IT, it will be combination of actually I4 current in the resistor 4 plus the current in the resistor X. Okay, flowing across resistor X. Okay, and from the questions, you know that IT is 6 ampere, and I4, okay, given in the voltmeter here, this will be 4 amp. So from here, you will know, if you use a simple mathematics, you will know that the current flowing across IX will actually be 2 amp. Okay, remember it's 2SF, 2.0 ampere. Okay, this is what we mean by current in the parallel branch, they will split. Okay, so the important thing that I want students or you guys to take note is that the current in the parallel branch actually will split out. So 1B, you look at the voltage, we look at the potential difference across different branches. Okay, one look at this particular circuit, you need to realize that the 12 volt potential difference across the battery, we have a name for it, we call it EMF, okay, electromotive force. Okay, so electromotive force is 12 volts. Okay, this particular set of battery will actually power the entire circuit, which means the energy given needed in this particular branch in this particular segment of the circuit. Okay, this will be what we call Vy. And this particular segment of the potential difference, so what I will label is as V parallel. Okay, these two potential difference, okay, will actually, the sum of these two potential difference across these 2 points, these two segments will actually make up of 12 volts, because your 12 volt, your EMF is the battery. He's the source of your circuit. He will actually power up these two segments. So I can safely say that Vy plus V parallel will be equal to your potential difference, equal to your potential difference of the battery itself, which is your EMF. Okay, and this is the first equation that you have. Second thing that you need to realize is that you have a parallel branch here, two resistors in parallel to each other. So when you talk about parallel branch, one of the trait characteristic of parallel branch is that the branches are the same. So I can safely say, let's say I call this branch 1. Okay, so this I call R1. Okay, this will be R2. Okay, one of the trait of parallel arrangement is that the potential difference across the first branch will be the same as the potential difference across the second branch. Okay, so because the resistance of the first branch is across these two nodes, these 2 points, then the potential difference of R2 is also across the same 2 points. Okay, and since the 2 points are actually the same points, that's why my potential difference across 2 and across 1, they will be the same thing. And since the potential difference across the parallel branch, where is the parallel branch we are talking about? The parallel branch referred to here. Okay, this is the parallel branch that we are referring to. And since these two parallel branch is also across the same 2 points, so I can safely say that V1 is equal to V2 and is also equal to V parallel. Okay, and with this, you will be able to answer the question whereby the question asks for what is the potential difference, what's the reading in voltmeter Z. Okay, voltmeter Z. Okay, from a simple analysis, you will know that voltmeter Z here, okay, will be actually equal to 4 volts. Why? Because V1 is actually 4 volts. And since Vz is 4 volts, so if you look at the circuit, okay, with this second equations, with this first equation, you will find that since, okay, EMF is Vy plus V parallel, and you have found that your Vz, okay, is 4 volt, which means your Vz, okay, which is also your V2, which is also your potential difference across the parallel branch, you will know that this particular guy is actually 4 volts. Since your EMF is 12 volt, okay, you will be able to find the potential difference, okay, or the readings of voltmeter Y. So you will simply, voltmeter Y will be 12 minus 4 will be 8.0 volts. Okay, same thing, 2SF. Okay, you can leave it to 3SF also can. Okay, but here what we have is the first two questions that we are living with. The first two questions, 1A and 1B, we are looking at the identifying simple parallel and series properties. Okay, current remain the same in series. The potential difference in parallel branch remain the same, okay, across the branches. Okay, now we look at question 2. Question 2, we look at a simple circuit whereby you have 3 resistors, 2 ohm, 3 ohm, and 5 ohm. And you have this ammeter, which is supposed to be a ideal ammeter, which means it has 0 resistance. So you can just treat the ammeter here as if it's a piece of wire, not affecting the circuit. The EMF of the circuit is 2 volts. Okay, now 2A, you have this term what we could known as effective resistance. Okay, effective resistance here, take note, it's just an anonym of total resistance in the circuit. So sometimes questions like to use total resistance, sometimes like to use terminology like effective resistance. They actually refer to the same thing. Okay, total resistance. Okay, if you cannot see this, if you cannot identify the arrangement of the circuit, you can actually simplify it. For example, Okay, let's do a redraw. Let me redraw a circuit. Okay, so let's say I have the battery. I will have the battery here. So this will be my 5 ohm. This will be my 3 ohm. So what we are doing, or what I'm doing is I'm actually going to redraw this particular wire. What I'm going to do with this particular wire is I'm going to extend it. I'm going to lengthen it such that it will actually long enough, such that it will have allow me to drop this 2 ohm resistor down on the floor. Okay, so when it's on the floor, this 2 ohm resistor, it will look something like this. Okay, so if you look at the circuit now, you'll find that this particular circuit, 2 ohm, 3 ohm, and 5 ohm, they are actually side by side, or what we call in series with each other. And we talk about in series, the formula that for series, the resistance will just add up to each other. A simple addition, 2 plus 3 plus 5, it will be 10 ohm. Okay, this will be simple effective resistance, okay, for the whole entire circuit. Then after that, what we are looking at, yeah, find the current in the main circuit. Find the current in the main circuit means effectively let's say I label it IT. Okay, basically I want to find IT, current flowing in the circuit. Same thing, if you look at this arrangement, if you look at this particular arrangement, I can, after finding RS, what has happened to the circuit, or what are you going to do with the information? When you talk about summing of resistance, you are actually combining the resistance. So instead of, like so-called, I will say, instead of buying 3 particular resistors, 3 ohm, 2 ohms, and 5 ohm, now because you have the effective resistance ready, I can actually shorten or reduce the circuit into a single resistor called RS, or we can call this 10 ohm. So instead of me buying 3 different resistors, I can just buy a single resistor 10 ohm, which perform the same function as 3 separate resistors in the first case. Okay, so that's the beauty of us finding effective resistance. Okay, I want to reduce the circuit, but when I reduce the circuit, it has the same function. So this is still IT. This is my 2 volts. Okay, so if I want to find IT, I would say the easiest formula is to use Ohm's law. V equal to IR. Okay, Ohm's law, like I told you in class, okay, Ohm's law, I would say that I'll term it as a selfish law, whereby if you want to find IT, you need to use the resistance RT, and you want to have the potential difference across the total resistance. In this circuit here, you have to realize that the IT is also known as EMF of the circuit. IT is what you want to find. Okay, so I want to find IT. So RT, how about RT? RT, you know already. RT is found in your part A, okay, which is your RS. Okay, so here you have a simple math whereby you look at 2 volts. Okay, IT, RS will be 10. Okay, so IT will have a simple addition of 2 divided by 10. It will be 0.20 ampere. Okay, so this is what we are looking at. Okay. Under your arrangements here, just take note, when you look at the particular circuits, so far what we are looking here is that, the arrangement that we are looking at when we analyze circuits, we are looking at the resistance, we are looking at the current flowing through the branches, we are looking at the potential difference. So normally, like what I remind you in class, when you analyze the circuit, always look for the V, the I, and the R. Okay, so the V of the V and the I, V, I, and R of individual branches, and also the V, I, and R of the entire circuit. Okay, so this is like I would say a rough guide to see how we analyze the circuit rather than just going around blindly. Okay, so now let's look at question 3. Okay, question 3, same thing. Before you do anything, okay, let's reorganize the circuit. So you will know that the circuit here, you have 2 resistors up and down, or I say in parallel arrangements. So what the easiest way where we do is let's combine them first. Okay, so if I'm going to combine them, okay, this is my 2 volt battery. When I combine them, this is what we call your R total. Okay, this is what I've done when I combine them. Okay, just reminder, effective resistance is referring to total resistance. Okay, so once you combine the circuit, it will become a single resistor called RT. Okay, so like most students, you will know, you are required to know the formula for parallel arrangements. Okay, so for parallel arrangement, the formula will be 1 over RT, 1 over R parallel over RT is equal to 1 over resistance 1 plus 1 over resistance 2. In this case, this will be 1 over 2 plus 1 over 5. Okay, this will be 1 over RT. Okay, and 1 over 2 plus 1 RT. So what are you doing? Is after that, once you get your answer, you are going to flip it over. Okay, so let's do a simple math. Use your calculator. 1 divided by 2. Okay, half or half plus 1/5. So what do you get? Okay, you get 7 over 10. Okay, so 1 over RT is 7 over 10. Remember, this is not your final answer yet. Okay, this is not your final answer yet. You don't want 1 over RT. So I want RT. So I need to flip the fractions. Okay, I need to flip the fraction. So now RT will be 10 over 7. Okay, 10 over 7, if you look at it in 2SF or 3SF, it will be 1.43 ohms. Okay, so this will be the effective resistance of the circuit. Okay, so remember to use resistance formula for parallel is important that you remember your workings that eventually you will need to flip the answer because the answer require you to start off with 1 over RT. Okay, but eventually what you are looking at is you want actually RT. Okay, of course, there are various ways of presenting your answer. So different teachers or different books will actually do it differently. But the idea, the mechanics behind it is always the same. Okay, the formula runs this way. Okay, now we look at the main circuit. So what's the current in the main circuit? Here, the main circuit refer to same thing, IT. Means the current coming out from the battery. Okay, which is here. So let's use another color. Okay, so the current coming out from the battery, IT. So current out coming from the battery, IT is the same. Okay, same thing in the series branch. The current across the resistance is the same. Across the circuit is the same. So same thing. I would say the easiest formula is you look at this particular circuit. Okay, because this particular circuit has some important information. Okay, it has one useful formula that we always, or sometimes we tend to forget. Okay, but it's one of the easiest and the most useful information, which is VIR. But what you are looking here is I'm looking at the final resistance, the total. So if I'm looking at the total resistance, I'm also interested in looking at the current flowing across the circuit, the total current, and the total potential difference in the circuit. In this case, your total potential difference is actually what we call EMF. Okay, so IT remains with 1 you find. RT, you found it already. RT, you found it is 1.43. Okay, so if you do a simple mathematics, this guy, EMF will be 2 volts. Okay, IT 1.43. So you can find IT you doing simple mathematics. Okay, and you'll find that IT is actually 1.4 M. Okay, 2SF or 3SF. Okay, so what we are looking here is we are looking at the first step that you look at in any circuit, you try to transform the circuit to something useful, and at each particular circuit here, after you transform, okay, remember to look out for important formulas or useful formulas that you want. It might be useful for your calculation later on. And one of the reminder that I need to tell you students is that remember is that when you look at solving theory questions like part A, part B, part C, remember to track your questions, because sometimes, like example, if I have let's say if I'm looking at a multiple part question, I have part A, part B, part C, part D. Normally, like individual part A, part B, part C, part D, they are actually correlated. So your part B answer actually relies on part A, or it could be a way whereby your part D answer actually depends on part A and part C. So it's not as if like you are starting each part from scratch. Okay, so you need to remind yourself to look at the correlationship between all the parts of the questions. Okay, now for question 4 now. Okay, question 4, you have a slightly complicated circuit whereby you have 3 resistors, two resistors in parallel to each other, and 1 resistor that is in series with the other. Now, the common question that we always have is I'm looking at the effective resistance, the total resistance. Okay, so we look at total resistance, and after that, the question says find the current. Okay, Now, for summing of resistance, like I mentioned in class, one of the common trick that I always do, I always remind myself is that when I sum resistor, I can only sum, I always tell myself, I can only sum, I can only apply the formulas if I am 100% sure of the arrangement of the circuit itself. Example, this particular resistor seems like it is in series with 5 ohm. Because they are side by side beside each other. Okay, but you need to realize that when I talk about series, it means they are only side by side, alone, perfectly alone, left and right. So which means I'm looking at there's nothing below it. There's nothing below here. There's no other resistor above it. So this is what we call a series resistance, where the resistor are in series. But you come to look at the arrangement. Although 2 ohm and 5 ohm, it looks like they are side by side, but there is something at the bottom here, which like I would say is not the same as the arrangement here. So it's like, it's a bit like similar to series, but it's not series, 100% series. So in case, when you have this doubt, okay, then you should not sum that particular set of resistors. It means there is some other reason, or that way of summing the resistance is not sure. So you look at other arrangements. So example, I look at 2 ohm and 3 ohm. It looks like parallel. So same thing, do a check. Okay, so what is the parallel branch? For parallel branch resistor, usually is what we call top and bottom, meaning they are like up and down of each other, and nothing on the left, nothing on the right. Okay, so in this case, this particular arrangement actually coincide with the parallel arrangements, the standard parallel arrangement. So I can effectively say that 2 ohm and 3 ohm are actually parallel to each other. Okay, so once I have this series arrangement, once I have this parallel arrangement, I will realize that R parallel is actually in series with my 5 ohms. Okay, so I will sum it part by part, section by section. Okay, so the first thing I do is I will actually sum the resistance first. I'll sum R parallel first. Okay, I'll do the parallel arrangement first. So it will be 1/2 plus 1/3. Okay, I'll sum it first. Okay, because I am very sure that this is a parallel arrangement. So same thing. So we end up, remember, once you get the answer, okay, 1/2 plus 1/3, use your calculator. Okay, you have 5/6, 1/R parallel. After that, remember to invert the fraction or invert the answers. Okay, so because I want R parallel, which is 6/5, which is 1.2 ohms. Okay, then you don't end here, because what the question wants, the effective resistance, the total resistance. So here you must continue. Okay, so you have R total will be R parallel plus R5. This is what I mean by series. Okay, 5 ohm is in series with the parallel branch. So it will be a simple 1.2 plus 5 ohm. It will be 6.2 ohm. That will be the RT. Okay, so effectively, the moment you found RT, what you have done is actually transform the circuit, okay, from a 3 resistor circuit. Okay, you have find R parallel first. This is 5 ohm. This is R parallel. Then after you transform it further, okay, to be a single resistor, which is what we call RT, which is still, the EMF is still 2 volts. Okay, now to continue with the question also says find the current in the main circuit. Main circuit refer to where? In the diagram given, main circuit refer to the, let me use another color. Okay, main circuit refer to the current coming out from the battery, which is IT. Okay, so if you transform the circuit, IT will still be the current coming out from the circuit, from the battery, which is still IT. It will be current coming out from battery, no change. Okay, so to find IT, same thing, go back to the basic. You look at the common question that we use, V equal IR. But now I will put my attention on to the last arrangements. Okay, because I know that for the last arrangement, if I use Ohm's law, is I want IT, I need the resistor RT, I need the potential VT. And same thing like I mentioned before, same as other case, it happens that VT is actually the EMF. IT, what you need to find, and RT you found already is here, 6.2. The EMF here refer to where? The 2 volts. So from here, you can actually find the answer for current in the circuit, which is IT. It will be simple math, 2 divided by 6.2. The answer will be 0.323 ampere. Okay, 3SF with units. Okay, take notes. Okay, one of the common mistakes students make is this. Okay, whenever you have intermediate working like this, like RT, intermediate working. Okay, please remember to put your units. So you shouldn't just end up here. You should actually write your units. Okay, write your units, ohms. Okay, write your units. Okay, so intermediate working, remember, always need to have units. Okay, intermediate working, need to have units. Okay, calculations, whatever formula you perform, that number actually represents something. So that particular item should have a unit. Okay. Now, then we move on to question 5. Question 5, if you look at the definitions, okay, where I look at definition of current, current is loosely defined as the rate of flow of charges. Okay, flow of charge per unit time. Some students ask me, hey, how come C is the answer? B seems to be correct also. Okay, now B is actually one of the way of defining current. But to be exact, is that B define a particular type of current. Then that current is what we call a single charge in 1 second. Okay, so this particular definition B actually define. Okay, it actually define a particular type of current, which is 1 amp. Okay, so option B actually refers to the definition for 1 ampere. Okay, so if the question asks for definition for 1 ampere, will be the amount of coulomb, the amount of charges flowing through a given point in 1 second. Okay, but since the question asks for a generic answer, generic definition for current, so the necessary or the relevant definitions will have to be given. So that's why C is like, I would say B and C are correct answer, but B, I would say B answer the question itself. Okay, so A, B and C are correct answers. They are correct phrasing, they are correct facts. But C answer the questions. Okay, so that's why C is a better choice here. Now, for the arrangement here, I will not dwell too much, except for the arrangements. Okay, so I will not beef out all the necessary working. Now, if you this particular arrangements, okay, one of the easiest ways is to actually rotate this option A like maybe 90 degrees, so it will become this way. So you'll find that all the resistors are actually connected in parallel. Parallel arrangement, remember, it refers to the up and down arrangements. Okay, nothing on the right, nothing on the left. Okay, so this is what we call R parallel. So in this particular question, question 6, you have to actually look at the calculations. Okay, you have to calculate the thing. Because the question says I need an effective resistance not greater than 12. Effective greater than 6, okay, but less than 12. So my RT preferably will be bigger than 6. Okay, lesser than 12. So the only way to do that is to actually calculate individually. So this guy is parallel. So by all means, go ahead and use the parallel range formula. 1 over R parallel equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, then you have an answer. Then same thing for option B is the same as I would say question 4. Okay, question 4 whereby this is the parallel arrangement first. So you find the R parallel first. Then after that, R parallel. So the first step here is you find the R parallel. Okay, 1 over 10 plus 1 over 10. Objective here is the working, you should be finding R parallel towards the end of the day. Then after that, the next part you do is the R total. R total, you'll find that R parallel is side by side, so in series with the 10 ohms. Okay. So these are what I mean by the particular arrangements, how to find the effective resistance. Always remember, for those find effective resistance, to find the total resistance, you can only add the components that you are 100% sure of their arrangements. Okay. C, straightforward series, so I won't dwell too much. D, okay, just take note, D, these two particular resistors, they are not in series. They are not in parallel to each other. Okay, although they have that arrangement, parallel arrangement, up and down arrangements, it seems that way, but somehow that this 10 ohm seems to be like in the wrong place. Okay, remember parallel arrangement, it should be one perfect or one resistor perfectly above each other or below. Only one resistor is above or below each other. Nothing else on the left, nothing else on the right. So in this case, you cannot sum these two resistors here. Okay, so you cannot sum. Okay, but you are very sure that you should be very sure that these two are in series. So you should sum them first. So after summing them, you will have this arrangement. So this will be a R series, this will be a 10 ohm. So you have you need to sum the series first. Okay, RS, submit first, you have 20 ohms. Then after that, you'll find that this particular arrangement, they are in parallel to each other, up and down arrangement, parallel. So here, same thing, you adopt RT, okay, sum the resistor, 1 over RS plus 1 over 10. After that, move on with your math and eventually remember to flip the fraction to find me RT. Okay, so if you do your due diligence on your working, you'll find that the answer here is actually D. D will be the one, D will be the one that will fit the answer. Okay, D. Okay, there is more than 6 but less than 12. Okay, please remember, okay, to try out, to get your hand dirty and try out the arrangement, because sometimes you does tend to make careless mistakes, okay, in the calculations. For 7, okay, 7, the arrangements, just take note, the ammeter A1, A2, the arrangement A1, A2, they are ideal. So the ammeter would just behave like a piece of cable. So you can just ignore it, the ammeter. So you can just take it as this is a piece of cable here. Okay, it will not affect the circuit. Okay, so same thing. If you can't see the arrangements, I suggest that you like rearrange the circuit. Okay, lengthen the wire. So what I'm going to do now, in case you don't, you can't see it, I'll lengthen this particular cable here. So if I lengthen it, the arrangement will look like this. This is my 10 ohm, 15 ohm, 10 ohm. Okay, what I'm going to do now is, let's use a different color so it's easier to see. So I'm going to lengthen this cable. So I'm going to lengthen it all the way here. Okay, I'm going to lengthen it here. Okay, then the resistor 3 ohm will be here. Okay, it's still the same, connected here. So this will be my 3 ohm resistor. Oopsie, what have I done? Oopsie. Okay, oh yeah, okay, it's back here again. Okay, so what I do is, okay, I lengthen the wire all the way here. Okay, so if you lengthen the wire, I would say it's fairly obvious that these 3 resistors, they are arranged in the following format. It's like 15 ohms is parallel to 16, is parallel to this 10 ohms. Then after that, this set of resistor, wait, let me use a different color. So this particular set of colors, or this is what we call R parallel. It's in series with 3 ohms. Okay, so if you look at the effective resistance, okay, there will be the effective resistance, the total resistance is in series. Okay, R parallel is in series with R3, the 3 ohm resistor. Okay, so if you work out the math for R parallel, okay, please go ahead and try, okay. Then you will find that you will have an answer for RT. Okay, then what you are going to do is the question asks for the EMF of the battery. EMF, or commonly known as EMF, or what we call V total. Same thing, let's use Ohm's law. Okay, Ohm's law will say that V equal IR. If I want VT, I'll have RT and IT and RT. Okay, so what is the current in the circuit? Where is IT? IT refers to the current coming out from the battery, IT here. Yeah, IT. And based on the questions, the ammeter is 1 amp and 6.6 amp. Okay, now take a look. Okay, the resistor, the 1 amp is, A1 is 1 amp. Okay, A2 is 0.6 amp. Now take note of the arrangements is this. Okay, where is 1 amp and where is 0.6 amp? A2 is the current flowing in 10 ohm, so it will be here. Okay, so I'll use different color so that we could synchronize. Okay, so this will be 0.6 amp. So this will be your 0.2 amp. Okay, so where is your 1 amp? 1 amp here is after the current come out at the node, they merge back. So this is the current returning to the battery. So 1 amp is actually here. 1 amp is actually here, IT. Okay, 1 amp is the current that is going back to the battery. Okay, so from here you can see that IT going back to the battery, okay, is actually 1.2 0M. Okay, take one of the common mistakes that students make is that they actually thought that the 1M and 0.6M are current in individual branch. So IT should be 1 plus 0.6. So common mistake they do is they assume IT is actually 1.0 plus 0.6. Okay, if you make this mistake, it means that you actually are not sure of about the arrangement. So you need to revisit the circuit itself, okay, to make sure you know how are the circuit arrangements arranged. Okay, so if you are sure, you will know that actually IT actually refer to only 1M only. Okay, so IT is actually 1M. RT, okay, you found it in the question above. You found it here, this RT, plug it in. You will be able to find EMF straight away. Okay, and if you found it, you'll find that the answer will be C. Okay, 9 volts. Okay, go ahead and try. Okay, go ahead and try. Okay, if you have meet any problem along the way, any questions, or if my answer is wrong, okay, feel free to leave your comment below. Okay, so that I will know that which answer I need to relook or which area I need to improve on. Okay, by all means. Okay, because sometimes my answer I do make mistakes along the way. Okay, now question 8. Question 8, yeah, I would say it's an interesting question. Okay, although it looks like, so where the question says that B1, they are identical bulb. So what happens is when the switch is closed, both switches are closed. Okay, both switches are closed. Okay, by right, it looks like the current is going this way. Okay, it's just a simple current. Okay, but take note, this is not the case because you have a line here, you have a wire here. This wire is what we call a perfect wire with minimum resistance or R equal to 0 ohms. Okay, so which means that at this particular branch, okay, when current come out from the circuit, okay, when it reaches this particular node here, okay, by right, it should actually divide himself and go to individual branch. Okay, but here take note, because this particular branch is a perfect wire, if a wire with no resistance at all, 0 ohm free, I would say it's the best cable, best path in the world. Okay, so because it's the best path in the world, your current will actually, or all your currents, all your electrons will actually divert their attention, okay, to the path here. So in fact, IT will actually flow here because it's the best path, it's the most comfortable path for all the current. Because why? Resistance is 0. The resistance there is minimum, is 0. Okay, so mean they don't resist current. So which means all your current will actually fly to the electron. They will actually be more than welcome. They will be most eager to go this particular branch. So as a result, IT will actually be traveling in the lower branch, in this highlighted branch. And because of this, your B1 and B2, no current will flow, even though it's a closed switch. But no current will flow at all. They will actually bypass. Okay, and because of that, both your light bulb will not light up. Okay, so that's why your answer is A. Okay, just think note, this particular arrangement is different from this arrangement. Okay, if there is a resistance below, okay, if there is a resistance below, okay, it means neither path or either path are perfect. So which means when your current flow down to this particular node here, IT, your current has to make a choice to whether go the top branch or to go to both branch. Okay, and because both branch are not perfect, there will be certain resistance, there will be small amount of resistance in each branch. As a result, some of the current, some of the electrons will actually go to the first branch, and some of the current will go to the second branch. So that's why if you look at this particular arrangement, you'll find that if you have resistance in each branch, certain amount of current will flow through each of the branch. Okay, as for this question here, is because this particular branch is a perfect 0, the best path of all, 0. Okay, that's why all the current will flow in that path. None will go through the light bulb. And we have a name for this scenario when you have a 0 ohm resistance, okay, cutting across the branches, causing things to not light up. We have this name we call it short circuit. Okay, so effectively is that the wire actually cause a short circuit. Okay, short circuit in the circuit itself. Okay, which means instead of flowing through the light bulbs, none of my light bulbs actually works. Okay, but the sad news is current is still flowing in the circuit. Okay, because there is a path for it, and that path is a perfect path. Okay, so this, just take note of this. Now, for question 9, I will not dwell too much on the mathematics. Rather than I will actually look at the arrangements. I will show you, highlight the arrangement. I'll rearrange the circuit for you. But I still need you to get your hand dirty to actually round up, to actually add up the resistance itself. Okay. In the meantime, okay, I actually work out some of the answers for you. So if you want to check your answer, I'll write it down here so that it's easier for you to check. Okay, for part A is a simple one. Everything add up. So this RT, the answer here will be 22 ohms. Okay, RB. Okay, so you have for B, RT here will refer to 0.968 ohms. Okay, for C, RT will be 2.4 ohm. Okay, for D, RT here will be 7.73 ohms. Okay, for E, the RT here will refer to 5.5 ohms. Okay, so now I would say that most of you will not have any problem with, or should be familiar with part A, part B, and part D. Partly because part A and part B are the generics, is the most common series and parallel circuit. Part D, I would say you should be okay because we have been dealing with it in the previous example. Okay, so it will be the same. So I will actually focus my attention on part C and part E. Now for part C itself, okay, you'll find that the arrangements, what I need to do is I will lengthen this two cable. Okay, so instead of like a diamond shape here, I will actually make it a rectangular, straight cable like what you guys are familiar with. I'll lengthen the cable. Then I will have a 2 ohm resistance here, followed by a 4 ohm resistance. Okay, then I'll straighten it. So below I will have a 4 ohm this way. So effectively what I did was I actually straightened the cable on the sides. So this will still be the first branch, the top branch, nothing changed. After that, this is my lower branch. Okay, nothing has changed. Okay, except maybe the cabling. Okay, so now this is still the same arrangement. So now take notes. Okay, you can remember to sum. You can only add the resistance when you're 100% sure. So if you look at the arrangement, you will find that, okay, this two is what we call 100% sure. I'm 100% sure that these two is series because they are side by side, okay, to each other. So I actually transform the circuit to this. RS. Okay, the 4 ohm is still there. Okay, so RS, I would say a simple 4 plus 2, you'll be 6 ohms here. So I can actually straight away write here 6 ohms. Okay, then after that, I will further transform the circuit somehow. Okay, because I know this two is confirmed a parallel branch. Okay, the ideal arrangements, up and down. Okay, nothing left, nothing on the right. So I will have an effective resistance here, R parallel. Okay, here, which R parallel happens to be my RT lah in this case. Okay, so you can just, so if you look at the working for this, is a step by step. You find RS first, then you find R parallel, or what we call RT. Okay. Now for arrangement E, E will be like a slightly interesting arrangements. Okay, so let me redraw E first. Okay, I'll leave the resistor here. Okay, the good thing about having it online is that I can actually color code everything. That I don't actually need like physical highlighters. You know, okay, as much color as I want. Okay, so for part E, okay, if you are not sure about the arrangement, one of the easiest way that we look at is actually I will just tilt the arrangements like maybe 90 degree. Okay, so my arrangement will look like this. Okay, so sorry for the ugly drawing. Okay, so I'll just tilt it 90 degree. So let me like code it a bit. Okay, so I will say that this is this guy. Okay, then let me choose a nice one. So yellow one, yellow guy. This is yellow guy. Then maybe I'll do one more dipstick. Okay, so I would pink one. Pink one will be here. This will be the pink one. Okay, so once you tilt it, I believe you should be able to get the orientation. Now, so now what happens is, if you still can't see the arrangement, so what I do is just continue to rearrange. Okay, continue to rearrange the setting. So what I do is I will actually try to drop the green color and the yellow color resistor. So what I'm going to do is I'm going to lengthen the wire here. I'm going to lengthen the wire here. I'm going to lengthen the wire here. Okay, so now let's look at the arrangement first. Okay, so this one, let me code it first. Okay, so this is the arrangement, or maybe I'll add one code. It's easier. Let me look at the color. Let's try green color. Okay, so this dirty green. Okay, so this will be the dirty green. Yes, no, maybe I don't try green. It's maybe confusing when I pronounce green. So let's say gray color. Yeah. Do I have a gray color here? Can you see? Oh, maybe I get a darker shade. Okay, so okay, I'll get this shade. So this gray color, this will be the gray color. Okay, so this will be my gray color. So what I do is I'm going to drop the cable down. Okay, so now I'm going to lengthen the cable this way. Okay, so in terms of coloring, okay, so this will be the arrangement. The green color one will be here. The yellow color guy will be here. Okay, so now if you are still not sure, okay, of the arrangement, okay, then don't worry, you go one step further. Okay, so now what I do is I'll keep the top branch arranged out nicely. So this is the yellow guy. Oh, wrong color. Sorry. So this will be the yellow guy. Then after that, I have the green guy. Oh, where's the green one? Yeah, I have the green one. The green guy is here. Okay, then the middle guy is a gray one. Oh, this is like coloring contest. Yeah, the gray one is here. Okay, so now what I'm going to do is I am going to shorten this particular area of cable, shorten these two area, and I'm going to lengthen this particular cable here. Okay, so what I'm going to do, okay, starting from here, I'm going to lengthen it. Okay, I'm going to lengthen it. Okay, so I'll have the resistor, the first resistor here. Okay, then the black one, the black circle one, this particular area here, I will shorten it. Okay, then I'll have the resistor here. So you look at the color code. Okay, I hope it's clear. Okay, the middle guy, this pink color one, the pink color one actually is here. All right. Okay, now, so with all, yeah, it looks like a primary school coloring. Okay, now with all the transformations, now you have the final circuit here. So the final circuit here, I hope it will be clear to some of you that these three are in series. Okay, they are side by side, they are in series. Okay, you are perfectly sure this is in series. Okay, but one of the common mistakes some of us tend to make is this. Okay, we will think that this is series. Give me first. Okay, it's lagging. Okay, a lot of us or some of us will think that this is series. Okay, they look like series, they look like side by side. But take note, because of the middle guy, there is a branch at the bottom here. If it's the branch at the bottom here, right, it will not be series. Series, 100% series, it means that the resistors are like side by side, nobody on top and nobody below. Okay, only that arrangement is what we call series arrangement. So for our case here, we have a slight small branch at the bottom of the middle resistor, or what we call a gray resistor. So because of that, I'm not really perfect, 100% sure it's series. So because of that, please do not sum the top one. Okay, so please do not sum this particular arrangement here. So please do not sum this. Okay, so you will move on to another arrangement, another set, which is the black one. That's why I know this is R series here. So you sum this guy. So when you sum this, once you sum RS, you can transform the circuit again. Okay, let's draw here. Okay, where's the blue one? Where's the blue line? Okay, the blue line is here. This is RS. Okay, so let me color code it. Oh, I don't need pink, I need green. So this is green. This is yellow. Yellow is here. Then the last color I have is gray. Come on, where's gray? Where's gray? All right, gray is here. Okay, so now I transform the circuit this way. Okay, then after that, if upon analyzing the circuit, okay, remember you can only sum the result when you're perfectly sure. So now what we have is you look at the arrangement. I will know that this arrangement, I am perfectly sure this arrangement is parallel. Gray color resistor and the blue color resistor is parallel to each other. So this is what we call R parallel. Okay, so that's why you sum it first. Okay, so now with that, okay, if you sum it, you will find that, okay, now your resistor become this way. Oh, a bit too near. Okay, you sum it. This is your R parallel. So if you look at the color coding again, I don't think I need to do any more color. Yellow is fairly obvious. This is green, which is also fairly obvious. Okay, so now you will have three resistance side by side, and this particular arrangement is 100% series. Okay, and with that, this will be the last transformation. So with that, you'll be able to transform, or you will be able to combine all these three in series arrangement into a final big resistor, what I call RS, but some of you can call it RT. Oh, it doesn't matter. Okay, so when you look at the arrangement, we start off with, I will not say a simple circuit. I will say it's interesting circuit. We start off with an interesting circuit with this. Okay, you may not find the RT with one formula or with one loop. So that's why I look at how many transformations. I look at 1, 2, 3, 4, 5, 6 transformation. So you do it step by step. You transform the circuit, you sum it. You sum it when you're perfectly sure of the thing, and you just move on step by step, part by part. There's no need to hurry. Yes, of course, in exam, we are looking at timeline. Okay, exams, assessments, time, we need to do the question fast. But in this style of circuit, if you rush through, you tend to make more mistakes. So in this case, I would say that you going slow, transforming them step by step, you're actually doing it quite fast. Because you know that every step of transformation, because you know what you are doing, you are very sure of your answers. And because of that, you actually save time in checking your answer. There's no need to double check because I am very sure of my answers. So I would say that it's like doing slow is doing fast. Okay, if this makes sense. Okay. So for these particular questions, okay, please spend some time to, like, I would say, work on it. Okay, try it out. Okay, of course, I would say that the exam assessment resistor will not be so complicated, but what the heck, okay, it's practice. So it's like, why not just try out this simple circuit? Okay, try to prepare for the worst, hope for the best. Okay. Now, question 10. Okay, question 10. Let's take a look. Question 10, I think, is the last question here. Okay. Now, is it? Yeah. Okay. Question 10. Okay, same thing. They have the two light bulb of resistance 4 ohms, and they are 1.5. A battery is 15 ohms, 15 volts. Okay, same thing. If you can't see the arrangement, you want to, like, if you are familiar with like most textbooks or most books, we're looking at the battery is always on the top, the load, the component is always at the bottom. So what I do now is let's rotate the arrangements, like maybe anti-clockwise 90 degree, or I rotate it to the left. Okay, so it's like, yeah, to the left 90 degree. So I will have the battery on top here. R is here. Light bulb is here. Okay, so this will be an arrangement. Oh, so sorry for my ugly handwriting. So now, one of the common mistakes that we tend to make is that we will think, based on the question, this is 4 volts. Okay, light bulb is 4 ohms here. This is 4 ohms and 3M is here. Don't forget to bring the 3M over. Okay. Now, one of the common mistakes that we tend to make is this. Based on the arrangement, it looks like it's confirmed these two light bulbs are parallel to each other. Okay. And that's where the mistake lies. Okay. When we thought that these two light bulbs are parallel, we also infer that, or we also link it to say that the battery is also parallel to the light bulb because they are up and down arrangements. Okay. This is the first mistake, and it's one of the major mistakes that we look at, because you have forgot about the resistor here. There is a resistor here. Okay, and this resistor, it will actually hinder the parallel arrangements. When we look at parallel arrangement, if I say that battery light bulbs are parallel to each other, I will expect the light bulb batteries to be in up and down arrangements, nothing on the left, nothing on the right, but I have something on the right here, which is this R here. So that's why these forward batteries and the light bulbs, they are not in parallel. So if you still can't see that, you need to continue to rearrange the, I would say you need to rearrange the circuit again. So let's start off with, like, let's say maybe, let's say lengthen the wire. So let's do it this way. So let me lengthen this particular cable here. Where's my red color? I can't see, it's lagging. Okay, this is the red color one. Okay, so I'm going to lengthen this cable here. So where's the black? Okay, the battery is here. Okay, so this is my light bulb. Okay, so this is my 3 amp current. This is my 4 ohms. Okay, this is my forward battery. So now I'm going to lengthen the red color cable. I'm going to lengthen it all the way here. Okay, until here. Let's say I drop it in. So after that, I will have my resistor, which is here. Okay, and the resistor is connected to the node here. Or sometimes, okay, if you want, I can actually, since like the color is free, so I would say I will shorten this cable. Okay, I will shorten this like brown golden cable. So I will shorten it to be here. Okay, so they refer to the same. Okay, so now with this particular arrangement, okay, bear in mind this is R. If you look at the circuit now, you will find that there is one interesting thing. By lengthening the wire, you have not changed the arrangement. It's just a lengthening, it's just rearranging. You are just rearranging the wires only. The connections, everything is the same. Okay, so nothing has changed. Okay, maybe the length of the wire, that's all. That's the only thing that changed. You will see that for battery, these two light bulbs are still parallel, nothing has changed, but you will find that the resistor R is actually in series with this arrangement. Okay, or should I say R parallel? Okay, it's a green color. Okay, so your R parallel here is actually in series with your resistor R. Okay, and from here you will see that the 4 volt is the EMF, which everyone knows, or most of us know. This is the EMF. It is actually providing voltage. It's actually providing a potential difference or energy for the potential difference of resistor, and also the potential difference across, or the energy for the parallel branch. So if you rearrange the resistor from the last transformation, you will realize that the EMF is actually consists of V parallel plus VR. That's the first thing you realize. Okay. Second thing, you will realize that the light bulbs are parallel to each other. Okay. This is R parallel. And after that, you have R parallel series with resistor R. These are the two things that you realize, okay, for these arrangements. So after rearranging the arrangements, rearranging the cables, okay, you'll find that these are what the batteries and the light bulbs are not parallel to each other. They are actually in the mixture circuit. Okay, so just take note of the rearranging. Okay, rearranging your circuits is one of the, I would say, one of the powerful tools that you have in your tool bag. Okay, then after that, what you do? Okay, let's solve the questions. Okay, since the question says find the current in the circuit. Okay, find the current in the circuit. Okay, red color is right. Find the total current in the circuit. One of the easiest way that we look at is take a look at this 3M. This 3M is in the branch here. Okay, one of the tricks that here you have to take note is that the key questions is identical light bulb. Okay, since identical, I would say the resistor of one light bulb. Oh, sorry, the resistance of one light bulb. Okay, bulb A, bulb 1 is based on the question is the same as bulb 2. This important information they give us, it will mean that the current in light bulb 1 is actually the same as current in light bulb 2. Meaning, the current here is 3M given in the question. Meaning, automatically, I will know that because the resistance is the same, 4 ohms, the current in the second branch is automatically 3M also. Because the amount of resistance will dictate the current. Higher the resistance, lower the current. So if you have the same resistance, you will have the same current, which is the inert property of resistance and current. High current, high resistance, low current, vice versa. Okay. Oh, sorry for that writing. So in this case, you will know that the current in the circuit, which is IT, actually consists of I, current of the light bulb 1, plus current in the light bulb 2, which is 3 plus 3, which is 6.0 M. Okay, which is the answer. Okay, remember to put, remember to put 2SF. Okay, that's the other one we look at is the effective resistance of the light bulb. Okay, here, take note of the keyword, they say effective resistance. But here, because of the wording at the back, across the two resistance, the effective resistance here doesn't mean the total resistance. It just means the total resistance across the two light bulb. AKA, what they are looking for is this. What they are looking out for is actually R parallel. Okay, so same thing, you activate the formula, you know that they are parallel. So R parallel, 1 over parallel would be 1 over R1 plus 1 over R2, which will be 1 over 4 plus 1 over 4, which means 1 over R parallel. Oh, sorry. 1 over R parallel is actually half, which means that, remember to flip. Okay, remember to flip, which means R parallel. Oh, let me erase this. It's a bit ugly. All right, a smaller one here. So you mean R parallel after you flip, it will be 2 ohms. Remember your SI unit. Remember your unit 2 ohms and the SF. Okay, is 2 SF, 2 or 3 SF. So it will be 2 ohms. Okay, then find the value of resistance R. Okay, now the easiest one I would say that since you already have the resistance, the total R parallel. So with R parallel, you can actually find the circuits will actually end up to be this way. After you add up all the light bulb, okay, R, after you have add up, sum up all the resistance in parallel, the light bulbs, this will become R parallel, this will become R. Okay, these two light bulbs you sum up, okay, these two light up, okay, they will be R parallel. And the question says your battery is 4 volts. R parallel, you know this is a number which is 2.0 ohms. IT, what information you know IT based on the question. Remember what I just said, okay? Your part A, part B, part C, all the parts in the question are related to each other one. Okay, they are correlated to each other. So the total current given here is 6 A. So you actually know that the current here is 6 A. The current here is 6 A, which is IT. Okay. So now I would say you can use a simple Ohm's law. Simple Ohm's law, V equal to IR. Okay, but now I pay particular attention to I1 total. Total resistance, total voltage. Okay, so where is my total resistance? This will be my total resistance. These two in series. Okay, EMF, VT, V total is my total. This is my green color one, color code it. Then after that, my EMF or my VT is my EMF. So it happens to be 4 volts. Okay, so if you put the number in, this will be 4 volts. RT will be R plus R parallel. My I, okay, I will be pink color. Let's say I will be 6 M. Okay, pink color, color code it. Okay, so it will be 6M. Okay, so now you substitute the number in. Since R parallel, you know already. R parallel, you actually know. R parallel is there's number in it. So it's actually 2. So here you do your math. Okay, I will say 4 divided by 6 equal to R plus 2. Okay, is it 4? Yeah, give me a minute. Oh, sorry. Oh, my mistakes. Sorry. My mistakes. The EMF is not 4 volts. So sorry. Okay, the EMF is actually 15 volts. No wonder it looks a bit weird. Where's my color? Oops, so sorry. It should be 15 volts. Okay, the question says 15 volt. Pardon me. Okay, so it should be 15 volt. So sorry about it. All right. Okay. 15 volts. Okay, let me highlight it again. Color code it just in case. Okay, green color one. Okay, so this will be 15 volts. Okay, so 15 divided by 6. Okay, then after that, you do your math, 15 divided by 6 minus 2, your algebra. So you'll find that R will be 0.5. Remember 2SF, 0.50 ohms. Okay, so with this is the last questions that I have. Okay, so end of the day, this worksheet, what we are looking at for is what you need to look out for yourself is that the idea of how to analyze the circuits, how to transform the circuit. With each transformations, what are the formulas that are useful for you? What are the characteristics that are useful for you? And from there, you lay out the math equations that you have on your table. After that, you look at the questions. So part A will require these formulas, or part A will require this concept. You just take it from a tool bag, apply it. Then after the next thing you need to be careful is to remember the co-relationship between each part. Maybe in terms of assessment, the questions could be a long question, part A, B, C, D, E. So in terms of some of the questions at E actually require the answers at D, or the understanding at B, or maybe A, B, C will add up to be maybe needed to solve part D. So for circuits, the correlationship between each of the parts is actually very, very heavy. So while you do your questions, remember some of the answers that you need in that part. The previous part could be a helping hand, or could be a tips, or towards solving this particular area. Okay, so with this, I hope I would say it will be clearer to you. I will not say you will have master circuit, but I hope it will be clearer to you. So if you have any problems, okay, in doubts, okay, if I make any mistakes in my presentations, do feel free to leave a comments at the bottom, okay, or just text me, or maybe just email me for those who know me, okay, about the mistakes. Or if you need further help, same thing, leave comments or email me or text me, okay. If not, okay, remember to practice. Okay, assessment is around the corner. Okay, the O level is around the corner. Okay, so remember to practice. And if end up, okay, just let me know. Okay, last but not least, same thing. Any questions? Okay, if you want to get updated with the latest video that I have, okay, remember to click the subscribe button and the bell button below. Okay, so that you'll be alerted. You'll be informed of any videos that are uploaded that could be of interest to you. Okay, so see you.